All right, this is our last lesson for 7.4. We have an essential standard that is the same. We're dealing with domains, asymptotes, intercepts of reciprocal and rational functions and graphing those functions. We are learning about point discontinuity / holes of those functions today. So repeatedly, we have talked about in behavior, and we are also interested in knowing what happens to the function output, so my y value, as the inputs get closer to the points that are not in the domain. So the values of x that make the denominator 0. The function could become unbounded. In that situation, we would have some value in the numerator over x, and this would be a vertical asymptote. They could become unbounded or approach some y value, point discontinuity or hole, which is what we're going to learn about today, or they could do something else, which is beyond our scope. Okay, so in the past, this is what we would have. We are always checking that numerator to determine if when the denominator was 0, did I actually have a value in my numerator other than 0? Because at that point, we knew we had a vertical asymptote. But today we're going to see what happens when that isn't the case and I have 0 in the numerator. So point discontinuities or holes within rational functions, they can occur when both the numerator and denominator equal 0 at the same point. So when you plugged in and you found your value of x that makes the denominator 0, and we check the numerator, we're going to end up with this situation. And then we have to figure out what's going on. In those situations, we're going to find that hole by simplifying the rational function, determining that the rational function is not unbounded at that point. So and you'll see what that means by that, but instead approaches a finite constant. Okay, so let's say we found that the 2 was not in the domain, and when I had 2, my denominator became 0. If I looked at the simplified version of the rational function and plugged in 2 for that, we might find that I might have 1 over 1/2. And now I know that I have a hole at x equals 2 and y equals 1/2. So this will make sense as we work problems. We will draw an open circle at those x and y coordinates that we have found. Okay, so let's do some problems. When rational functions are graphed, this is important. All holes must be drawn and labeled with XY coordinates. If you're not labeling them, you're not going to get credit. Determine the domain asymptotes and zeros of all the rational functions and graph the rational functions. This is problem A. All right, so I know I'm probably going to need to factor this. I'm going to go ahead and factor this. That becomes x minus 2, x plus 2 over x plus 2. You can see that I can simplify that this particular function, and we're going to need to, but we'll get there in just a minute. So when we find our domain, if you recall, we need to determine what values of x make the denominator 0, and we do that before we simplify, and that will be -2. So x cannot equal -2. Okay, when x equals -2, my denominator is 0. We know that. When x is -2 and I plug it into my numerator, -2 squared is a +4. +4 minus 4 becomes 0. I have that situation where I have a 0 in the numerator and a 0 in the denominator. This situation needs to be evaluated further. This is not unbounded. I need to confirm if I have a hole. In order to determine if I have a hole, I need to simplify my function completely, which those +2's can cancel, and my function becomes y equals x minus 2. And now I'm going to plug in my -2, which is not in the domain, for x, and I get -2 minus 2, and so that is -4. So I have a number, a value. So as x approaches -2, y is approaching -4. -2, -4, I would actually write that down, is a hole. Okay, all right, let's continue. Vertical asymptotes. We had no vertical asymptotes because in no situation did I have an unbounded scenario, because when my numerator became 0, I did not have a discrete number in the, I'm sorry, when my denominator became 0, I did not have a discrete number in the numerator. Horizontal asymptotes, that's in behavior. And if I were to look at my dominant terms, it appears that I'm unbounded, but here's what I will tell you. This function is essentially x minus 2, and there is no horizontal asymptote because all of my points are on this line, x minus 2, except for my hole. So no, I have no horizontal asymptote. Oblique asymptote, if I have, I don't have an oblique as well. Zeros, I do have a 0. What values of x does my numerator become 0? And you would think that you would have a positive 2 and a negative 2, but negative 2 is not in my domain. So I do not cross the x-axis at negative 2 because negative 2 is not a part of my domain, but 2 is a 0. I do have an x-intercept. So how would I draw this? I have a hole at -2, -4. So let's draw that. There we go. And I cross the x-axis at +2. And my function is essentially a line, and it'll look something like this. There we go. All right, let's try another one. Why don't you try one? Welcome back. Factor this, you're going to need it. So when we factor that, I have x plus 3 and x minus 8 over x plus 3. This will simplify to x minus 8. So it's essentially a line, y equals x minus 8. What is the domain? Well, the domain are all values of x except for x cannot be equal to -3, because at -3, my denominator is 0. What happens to this function when x is at -3? That's what we want to ask ourselves. Well, if we plugged in -3 in the numerator, I get -3 squared, that's 9. I will get plus 15 minus 24, and that'll end up being 0 over 0. So I do not have a vertical asymptote at -3. I have to confirm what's going on. So if I plug in -3, I want to look at my simplified version. I find that -3 minus 8 is -11. So I have a hole at -3 when x is -3 and y is -11. And I'm going to write that down because I wish there was a line here for holes. So vertical asymptote, I don't have any. We just confirmed that the only x that's not in the domain doesn't have a vertical asymptote, but has a hole. Horizontal asymptote. Essentially, this function is simplifying to a line, and so I do not have a horizontal asymptote, nor do I have an oblique asymptote. And actually, you can confirm that you don't have a horizontal asymptote by looking at the two dominant terms. And x squared divided by x just leaves you with x. So I'm not approaching a finite number. And I don't have an oblique because it's just all my points are on this line. All right, zeros. Are there any values of x that make my numerator 0 and that are not that are in my domain? So you would think potentially, be careful, you might write -3 and a +8, but -3 is not in my domain. So the only zeros are located at x equals 8. So let's go ahead and graph this. And so I don't have a vertical asymptote. I don't have a horizontal asymptote, oblique asymptote, but I have a hole at -3, -11. So maybe that looks like right about there. And I have a 0 at x equals -8. So I'm going to have across the x-axis at 8, and it's essentially a line. And there we go. All right, let's do another one. Let's go ahead and factor this. I have on the top, I can factor out a 5. And on the bottom, I have x plus 6 times x minus 2. That will simplify to 5 over x plus 6. Okay, domain. Remember, we're going to look at the ones that are before we simplify to define what makes my numerator 0. So x cannot equal -6 or +2. Well, what happens to my what happens to my let me see if I can speak. What happens to my function as x is equal to -6? I'm going to actually look at my simplified version, and I can say 5 divided by, well, when x is -6, it ends up being 0. So I have a vertical asymptote because my numerator is not 0. So I have a vertical asymptote at x equals -6. Well, if x is 2, if I have plug in 2 for x and I look at my simplified version, I have 5 over 8. And that is not unbounded, it's a finite number. And so I have a hole at x equals 2 and 5/8. You could have also gone over here and done that. When x is -6, 5 times -6 is -30, minus 10 is -40. And then on the bottom, I would have gotten 0. So once again, I have a number other than 0 in my numerator, and I have a divided by 0 in my denominator. So I definitely have a vertical asymptote there. If I plugged in +2, 5 times 2 is 10. Minus 10, I have a 0 in the numerator and I have a 0 in the denominator. And so that's why we needed to evaluate what happened to my function in simplified form when x is approaching +2, and we have a hole. Horizontal asymptote describes in behavior. So let's take a look at that. In behavior, so I have to look at my dominant terms. I have 5x in the numerator and x squared in the denominator. So I can simplify that to 5 over x. And so as x gets really large, I actually am going to approach an actual horizontal asymptote at y equals 0. If I have a horizontal asymptote, I do not have an oblique asymptote. What values of x make the numerator 0? That will be a 0. And so we might find that 2 would be an answer. But be careful, 2 is not in my domain. So essentially, there are no zeros, none. So now we can go ahead and start graphing. Well, I have a hole at 2, +2 and 5/8. So let's go and put that right there. And there's my hole, and I've labeled it. I've also found that I have a a vertical asymptote at x minus 6. Let's put in my vertical asymptote. Anything else I need to do? Let's see, I have a horizontal asymptote at y equals 0. Well, to the left of this vertical asymptote, I know that I've got to do some investigation because I don't know if the graph is here or if the graph is here. So let's pick a number. Maybe x equals -7. So let's plug in -7. Easiest to look at my most simplified version of this function. So 5 over -1. So I have a -5. So I know that I'm negative. So I must be in this region here. That's all you need to do. To the right of my x equals -6, I've got to be approaching that hole. And so I have to be above the x-axis. So I've got to be approaching that hole. And to the left of that hole, I've got to be approaching x equals -6, and it becomes unbounded at vertical asymptote. So it's headed upwards. And then after the whole, it's got to be approaching again, y equals 0. So it looks something like that. You can confirm if you'd like to the right of that by plugging in a number greater than x equals 2, but it will be positive. Let's do D. Let's go ahead and factor. The factor, the top, I have, let's see, x plus 3, x minus 2. The denominator is actually 4 terms. Now, how do we factor a 4-term polynomial? That will be factored by grouping. So I'm going to look at my first 2 terms, and then I'm going to look at my second 2 terms. In the first 2 terms, I'm going to pull out an x squared. Can I pull out an x squared? Yes, I can. And I am left with an x plus 3. In my second 2 terms, I'm going to pull out a -4 because I want to have an x plus 3. So I pull out a -4 and I'm left with a positive x plus 3. Now I can group the denominator. I'll get x squared minus 4 times x plus 3. I have to continue because the denominator has a difference of 2 squares. And I will have x minus 2 times x plus 2 times x plus 3. Eventually, I'm going to probably need to simplify this, so I might as well go ahead and cross out my x plus 3s and my x minus 2s, and this will simplify into 1 over x plus 2. All right, now let's go fill out our chart. Domain, what values of x makes the denominator equal to 0? And I must look at that prior to simplification. And so let's list all of our x values. That will be when x equals plus or minus 2 and a -3. Now we have to determine what happens to our numerator when my x is approaching those values that are not in the domain. And I can, I personally would look at my simplified version and say, okay, when x is a positive 2, my y is actually approaching 1/4. So I have a hole at 2, 1/4. When x is approaching a -2, I get a 0 in the bottom. I have a number in the top, and therefore it's unbounded. And so I have a vertical asymptote at x equals -2. If I plug in -3 into this simplified version, I get 1 over a -1. And so I have another hole because as x approaches -3, my y value is approaching -1. So I have another hole. So those are not vertical asymptotes. I list them here as holes. I would have actually, and maybe a better way is to put it down here, but it's kind of a part of the, it should be next to that vertical asymptote because we're evaluating all of our x values that are not in the domain to determine if a vertical asymptote exists or if a hole exists. Now, horizontal asymptote, that describes in behavior, and I have to look at my dominant terms. I have x squared in the top, x cubed in the bottom, x squared cancels, I'm left with x in the bottom, and essentially that simplifies to 1 over x, and as x gets very, very large, what happens? Y goes to 0. Oblique asymptotes, if I have a horizontal asymptote, I don't have an oblique. Zeros, well, what values of x makes my numerator 0? That would be a -3 and a +2, except that neither one of those are in the domain. So it is not possible to have a 0 if the value is not in the domain. Therefore, we have done, this would be none, what we need to do in order to graph. Vertical asymptote is located at -2. So this is at x equals -2. Horizontal asymptote is equal to y equals 0. We have some holes that we need to plug in. So we have 2, 1/4. So maybe that's here. And we have one located at -3 and -1. So we'll say here. And now we need to look at our regions. We have one that's to the left of that vertical asymptote, and we know that x has to be approaching y equals 0. So we're going to come and head towards that hole and then become unbounded at x equals -2. To the right side of x equals -2, I have to be approaching that hole, and I'm coming from an area that's unbounded. So I'm going to look something like this and eventually head towards y equals 0. And I think that's it. We have one more to go. Give it a shot. Welcome back. Let's simplify the top. That's 3 times x minus 1. And in the bottom, I have, that simplifies to, or factors into x minus 1 and x minus 5. And we can get rid of that x minus 1, and I find that to be x minus 5. All right, domain. We have to look at it before we simplified. X cannot equal 1 or 5. Vertical asymptotes. Do I have a vertical asymptote when x equals 1 or 5? I don't know. Let's go plug that in. We can look, I personally would look at the simplified version and plug in 1, and I see that 3 over -4 is an actual value. So that means that as I approach 1, my output, my y, is approaching -3/4. So I have a hole at -3/4. If x is approaching 5, then I have 3 divided by 5 minus 5, that's 0. So that is unbounded. Therefore, I have a vertical asymptote at x equals 5. Horizontal asymptote, I look at my dominant terms. I have 3x over x squared. I end up with 3 over x. As x gets very, very large, I'm approaching 0. And if I have a horizontal asymptote, I don't have an oblique asymptote. And then, of course, what values of x make my numerator 0? Well, that would be a 1, except that 1's not in the domain, so I can't have a 0 at that location. It will not cross the x-axis since there is no point at that location. I'm either unbounded or headed towards a hole. Now, let's go and plot some things. We have a horizontal asymptote at y equals 0. We also have a vertical asymptote at x equals 5. And now we need to see, let's plot, do we have a hole? Yes, we have a hole at 1 minus 4. I'm sorry, 1 comma minus 3/4. So that'll be somewhere maybe here, 1 comma -3/4. And so that hole kind of tells you that to the left of that vertical asymptote, you're going to be underneath that horizontal asymptote. And you're going to do something like this, because as x goes to -infinity, I've got to be headed towards y equals 0. And after that hole, as x approaches 5, I become unbounded. To the right of x equals 5, I got to determine, am I above or below? Am I negative or positive? And so we're going to go ahead and pick a number. Maybe we'll pick 6. If we quickly, I would look at my simplified version, 3 over 6 minus 5, y will be a +3. So I've got to be maybe, well, I know I'm positive, so I'm above. And now I can hopefully see that I have something that looks like that. All right, that is the end of our lesson for today. I hope that makes sense. And reach out to me if you have any questions.